Now for the final talk, we're happy to have Johannes Henn, and he'll talk about positive scattering amplitudes.
Thank you very much. So this is work done together with Prashant Raman, who's a postdoc at the Max Planck Institute for Physics in Munich. And I'd like to tell you about surprising positivity properties of scattering amplitudes. So it's really a great pleasure to be back here. I used to be a member about 10 years ago. And somehow this topic, these kind of objects that I'm presenting today, they take me back to some of the things I started studying them while I was a member here. So that's of course very nice. But the viewpoint today is very different. So in a lot of my work, I'm interested in the analytic properties of amplitudes. What are the symbol alphabets that we've heard about at the conference? How do they come together? And I was interested in writing out these analytic formulas. But today we'll take a different viewpoint and actually got interested into plotting functions. So let's look at an example. So this is a plot taken from a paper by Lance and collaborators, which is a single variable slice of the remainder function. So a remainder function appears in 6-particle scattering in n equals 4 supermills. And this is it's generally a function of 3 variables, but here it's plotted along a single variable slice, so the variable u. What's really remarkable is, we've heard it earlier in this conference, that this quantity is known to very high loop orders. But here I just want to point out the fact, as it's also pointed out here, that these graphs look remarkably similar. So in a way, there's all this understanding and these calculations that go into producing formulas with millions of terms. And then it's a bit ironic, at the end of the day, we have these, I'm not allowed to say boring formulas because it's Lance's plot, but let's say not so many features. All right. And that even more remarkably, I mean, it's a little bit small here, but you see in this, it says here in the description, but if one goes below u equals 1, then the features always become indistinguishable. And in fact, later in the talk, I'll focus more on precisely that region. Let's look at another example. So now I'm allowed to say it's boring because these are taken from my paper. So this is the QCD cusp anomalous dimension, the angle-dependent anomalous dimension. It's parameterized through this variable x here, which is related to the scattering angle like so. And so we have here different loop orders of the QCD anomalous dimension and also the for-loop QED case. And again, you see the plot is pretty boring. I really have to zoom in here to begin to be able to distinguish what's going on. So in this talk, I'm going to propose a mathematical property of some functions, which is supposed to explain what's going on here. So let's now switch gears for a moment and let me just define something. So I'd like to talk about a class of function which is called completely monotonous functions. So what are they going to be? So we see from this plot here, these are all positive functions. So let's start with this. These are positive functions. But now I'm going to impose infinitely more conditions. I'm going to say that all the signed derivatives of these functions are positive. So it's just this neat condition here. So that means that, in particular, the first derivative is negative. So we have a monotonically decreasing function. The second derivative is positive. So we're talking about convex functions. And then there's infinitely more conditions, which I don't know how to put in words, but they have some mathematical consequences. And I'm going to claim, and I'd like to show examples in this talk, that these are quite abundant, actually, in quantum field theory. But before going there, let's now just have some fun and let's play with those functions. So here are a few first examples. 1 over x, 1 over 1 plus x. So with those, with a little bit of algebra, you could convince yourselves that those satisfy these properties. So these are CM functions. This ratio is already a little bit more complicated. We'll see in a minute how we could prove it. And then there's also more complicated ones. It's useful to know that this class of function has closure properties. So if you have 2 such CM functions, also the product is a CM function. Also, you can take convex linear combinations. Furthermore, you can take differentiation. You get another CM function. and also they're closed under integration as long as you choose an appropriate integration constant. So that these properties will be quite useful in understanding the CM property of some of the scattering amplitudes we'll see later. But in fact, there's something in a way even more powerful. There's a theorem which says that any CM function, it has to have a Laplace representation of a certain type with a positive or non-negative integration kernel mu. So that's very powerful because it's an if and only if statement. So for example, that allows us to see very conveniently the CM property of one of the examples I had earlier. So this function here, you can convince yourself that it satisfies, it has this Laplace transformation, or in other words, if you plug this in here, you get back that function. And so since this is manifestly positive, the condition is satisfied. Now, there's also a multivariable generalization of this theorem and of the definition. So it's very straightforward. You just say for a multivariable function, any sign derivative has to be non-negative. And here's an example which some of you might recognize from this one mass easy Feynman diagram. It's already a rather non-trivial function of dilogarithms and logarithms. And I claim that this is completely monotonic for any positive values of the parameters. We've seen a little bit how to prove that, or one way of proving it. But so now let me give you a preview of what I'm going to talk about. So I claim that this property is actually appears in many quantum field theory properties. And for me personally, my original motivation, or main motivation, is something called positive geometry. So in a nutshell, the idea is that certain scattering amplitudes in supersymmetric theories can be thought of as volumes. So volume intuitively, so I'm arguing in a hand-waving way, are positive. And you can also think that if you have such a volume and you change the parameter somehow, there'll be a notion that the volume increases or decreases. And so if you have control over how to do that, how to define your parameters, you can make it such that it decreases. I don't have an intuitive picture yet, what is the second derivative and the third and so on, but that's as good as it gets for now. And so there's some quantities, in particular these remainder functions I showed you in the first slide, where positivity has been found in the perturbative data. So in this talk now, I'm going to check those cases for these infinite further positivity conditions in the derivatives. So that's for those special quantities like the remainder function in n=4 Swinnerton-Mills. But then I'm going to argue that actually the CM property is much more widespread in terms of building blocks in quantum field theory. And so we'll see it as actually something very common in Feynman diagrams, which have a Euclidean region. And moreover, and this will be useful also for proving the property, it's closely connected to dispersive representations that satisfy certain conditions. So let's go from here backwards up that list. Let me start with an example of a dispersive representation. And that'll actually be useful to prove the CM property of a slightly non-trivial example we had earlier. So here's again this dilogarithm formula. So the idea is to notice that this function has the following integral representation. It's a double dispersive or Mandelstam representation, where essentially you have two factors which are there to produce for you the branch cuts along the negative real axis of a function. And then this is really the discontinuity. So if you had to derive this, you could notice that here these logarithms, they generate the branch cut, and then this is the discontinuity. And here I've written it just for, since the cut is on the negative real axis, I've changed variables, so here everything is positive. So this is a valid representation. And so now having this representation, the CM property is almost trivial to read off because, well, first of all, this is positive. And then you see once you differentiate with respect to x1 and x2, you just get this pattern of minus signs that appeared in the definition. So I find that quite remarkable. In this way, from this viewpoint, it's very easy to prove. But if someone just gave you the polylogarithms, actually not trivial at all. Right. So now let's go to Feynman integrals. So it turns out that any scalar Feynman integral that has a Euclidean region, again, has this property. Here's an example. Let's just take this bubble integral. It has this Feynman representation. What's key is that since it's a scalar Feynman integral, we don't have any non-trivial numerator here. And so the denominator is a non-negative function. That was the requirement having a Euclidean region. And also it's linear in the kinematic variables. So again, just as with the previous example, we can see by differentiation that we'll just get some minus signs times some positive function. And so therefore, this is Cm, again, for any positive value of x1 and x2. So this shows you that this is really a very widespread property of at least building blocks in quantum field theory. Now, it's actually interesting that there's a very nice paper by Mao Zeng who just used the positivity of integrals in combination with IBP relations to get some constraints and use some semi-definite programming to actually bootstrap the value of the integral. In fact, so that shows you that already just using positivity can be very powerful. Now here you can add to this an infinite number of more constraints. And in this way, you could get a more rapidly converging algorithm. All right, but that's not the main point of the talk. So let me move on from here. So now, in a similar vein, you can convince yourself that actually for many objects that we see in current studies, the same property holds. And again, it's nothing too special. For example, if you look at some example of a cosmological correlator integral, well, it's just something where you have a positive integrand, and again, the variables appear in such a way that when you differentiate, you get these sign patterns. So it seems quite trivial seen from that viewpoint. But again, it's not trivial at all if you look at the integrated answers. I already mentioned that, so my example was a planar Feynman integral. So it's true for all scalar, for all scalar planar Feynman integrals. It's also true for non-planar integrals that have a Euclidean region, which is the case when you have sufficiently general kinematics. And then you can see this property in stringy integrals. And also there was this paper which is called positivity certificates, where in particular it's shown that certain hypergeometric functions have this property. So just a recap, we've seen that we've discussed what completely monotonic functions are. I've argued that they appear in many building blocks in quantum field theory. Now I'd like to go back to the very first example and ask a question: what happens if you combine these building blocks? Typically, we'll not just have scalar integrals, but we have scattering amplitudes or observables that we're interested in. There are linear combinations which may have plus and minus signs. So these wonderful positivity properties could easily get lost. So let's study that in more detail. So I already said that the motivation is really the amplituhedron, and we're building off on top of that previous work where actually positivity had already been observed in several examples, including by Lance and his collaborators. So let me just say a few more words for those who have not followed this in detail. So the amplituhedron gives you the first hint because it tells you what the loop integrand is, and there's a statement that the loop integrand is positive in the amplituhedron kinematic region. So that's a good first piece of information. But then there's a worry. It's not so clear what happens when you integrate this over Minkowski space. And so at least I am not aware of a solid argument or even proof that this positivity prevails. So at that level, it's a conjecture what happens. But we have a lot of data, so it's interesting to look at it. And so this is what, in particular, Lance and his collaborators did, and also Nima, Andrew Hodges, and Jaroslav Trinka. And they found that, perhaps surprisingly, if you take this integrated amplitude, but evaluate it now again in the tree kinematic region, you find something positive. There's in fact a further subtlety. There was the first subtlety of what happens when you integrate over Minkowski space. There's a second subtlety which has to do with infrared divergences. So the object we're computing is actually not finite, and although we know very well how to remove those divergences, it's very tricky to talk about positive quantities and subtracting something off of them. So how much should we subtract off? Is the positivity preserved? And in fact, in Lance and friends, they found that actually at 4 loops, the definition of the remainder function does not stay positive, but we also found a modification which is called curly E, the so-called BDS subtracted remainder function, which they found preserves the positivity. So the way to think about it, that perhaps this BDS subtracted function subtracts off just a little bit less. So just what's needed to make it infrared finite, but preserving this nice property. And so we now take that Q and then investigate also the positivity of the derivatives. So let's look at this. So what is this tree-level kinematic region? Well, there's some inequalities on the 3 kinematic variables, like so. And so this is what I just said. Lance et al. Found that this quantity is non-negative. So what one actually finds to be non-negative is at each loop order, it's either positive or negative. So there's some -1 to the L, which there is. Okay. And they prove this either in certain kinematic limits or kinematic slices and also by numerical integration. I should say that very interestingly, they also found some evidence for monotonicity in a certain double scaling limit. So let's look at this in more detail. Here's again the plot from before. And now, in fact, when we make all 3 variables equal, this amplitude region actually corresponds to U positive and smaller than 1/4. So indeed, we need to look very much in this region. Actually, I was a bit confused about this. We even fall off the below the axis. There's a little subtlety that here one divides by something which is negative, and so it becomes positive. Everything is okay. So if we zoom in here at 2 loops, this is the plot we get. So this is like, you can think of it as a magnification of that region, and we see exactly what we like, something positive, decreasing, convex. But now we'd like to prove it. So let's see about this. Let's start at 1 loop. We actually almost have all the ingredients we need. So it turns out that this 1 loop function that they introduced, it's a sum of 3 single variable functions, which is just this Li2 here. So we'll just need that. So gamma in general is, this region is more complicated, but we'll just need that the variables are smaller than 1. So now let's prove this, prove that this function is CM. We're going to use a little lemma. We already know that these 2 functions are CM. And we also know that their product is CM. So we're going to remember this. So this product is CM. But now we just compute the first derivative, the signed derivative of this, and we see it's that function over there. So then we can use closure under derivatives. And the only thing that remains to be proven, rather we want to use closure under integration. And that requires now just to prove that also the boundary value is the correct one. So we have a function that's decreasing, and we want to prove that it's actually positive on the interval from 0 to 1. So by showing that it actually vanishes at 1, that's all we need. So that concludes the proof. So therefore, we've proven that this property holds at 1 loop. Okay, let me go to 2 loops, but now the 2 loop functions are rather complicated, so I'm just going to be sketching the proof. So we prove it as follows, and using the following step. Here we were struggling a little bit, so we really had to throw everything we knew, all our tricks at this function to prove a property. So the first trick is that we use some integral representation that was derived many years ago. So one can represent this remainder function in terms of some very nice double pentagon integral that Nima and friends introduced, plus some single variable functions. And then first of all, we can prove that the single variable function with that subtraction I told you earlier about, that those are CM, and there the proof goes very much along the lines I showed you earlier. We take a derivative, we derive a dispersive representation, everything can be shown very neatly. And then secondly, we prove that this double pentagon function is also CM. For that, we use another representation from that same paper, where essentially we show that this part here is just an integral of a hexagon integral, which is itself CM. So again, we use this closure property. And then there's another Feynman integral. It's a so-called pentaladder integral. And for that, we have a more direct proof, again, that it's CM. So again, I'm just sketching it here, but to give you a feeling for it. So the upshot is that here we can prove rigorously that the two-loop function has the CM property. Now, of course, we wanted to go beyond, but our analytic strength of proof might require help from mathematicians. So we stopped here and now switched to numerics to gain some further understanding at higher loops. And so here's some plots. In fact, we at free loops we checked the values of a function, which was already known, but also of the first two signed derivatives over some range of values in u, v, and w. And they all confirm this hypothesis of CM property. We're also working on the for loop checks, but it's a bit complicated because there's many Goncharov polylogarithms of high transcendental weight. And anyway, so here you can see just the function again, and you see this typical property of decreasing and convexity. Okay, so that's what I want to say about this remainder function. Now, I said in the beginning, I mean, this brings me back to many different projects, in fact. So we looked actually at many interesting quantities in quantum field theory. And so here's a list of things we looked at and where we have evidence that this property holds. So in particular, there's an object called which is the 4-point Wilson loop with a Lagrangian insertion. This is known up to free loop order, so there we've proven this analytically. I already showed you the case of the angle-dependent correspondence dimension. So actually, sorry, this is a different one in n equals 4 supermills, up to 4 loops. There's some 4-point amplitudes with masses on the Coulomb branch. And furthermore, we've looked at 4-point correlation functions. So for all of those, we have either numerical or analytic evidence that this property holds. And finally, and this is again one of the plots from the beginning, the property holds for free loop QCD anomalous dimension and the for loop QED one. So just to summarize, I showed you evidence that completely monotonous functions are relevant for many objects in quantum field theory. It's interesting that in some cases, there's a really elementary explanation. You just look at the Feynman parameterization, it's totally obvious that this property holds. But in other cases, we don't really know why it's supposed to hold, or even if it holds, like the cases where the motivation was the amplituhedron. And so there it remains to be proven, and therefore there's a lot yet to be done. So I'd like to conclude just with mentioning some of the directions I find exciting. So we already looked at some data, but there's much more data to be looked at. And as I said, in some cases, we only have numerical evidence. So clearly, it's very worthwhile to understand for those types of transcendental functions, for example, how can we prove a CM property? How can we make this more systematic? But there's also more cases to look at. So in particular, there's also evidence for positivity for non-MHV holistic configurations, and we haven't explored those yet. There's also Wilson loops with Lagrangian insertions at higher number of points, and maybe you have your favorite object that you like to look at. Then a second point has to do with understanding why this property holds from first principles. So can we make this connection to positive geometry more concise? Perhaps knowing that there's more to be looking for, so maybe that helps in some way. So somehow, ironically, I have a feeling that, at least for me, it was sometimes hard to prove that a certain function is positive. But if I know that I have to prove that all of its derivatives have this positivity feature, it's sometimes even easier because one looks at it in a different way and looks for different method of proving it, like this Laplace transform, for example. So in the same way, I mean, can this guide us to making this link to positive geometry? There could also be a physical explanation in some cases related to dispersion relations, where the kernel, for example, in the Mandelstam representation has certain properties. And then finally, okay, let's admit this property is there. What is it good for? So I already hinted at the fact that, well, it could be useful for some numerical approximation, some semi-definite programming, if you wanted to interpolate your function or in some way approximate it. And finally, let me mention that we studied this. Typically, we have this property in a certain range of values, for example, from 0 to 1/4 in this equal variable case for a remainder function. So what does this property tell us for other regions, like for example, this whole region from 0 to 1 in the plot that we had initially? Or for physical applications, let's say you want to study, I don't know, 3-jet or 4-jet production, you typically like to analytically continue to some scattering region. So if a property holds in the Euclidean region, what does it imply mathematically for those other interesting regions? So I'd like to leave you with those questions. Thank you very much.
Thank you, Johannes. Do we have questions?
Nice talk, Johannes. Do you think also one should maybe analytically investigate these multi-Laplace transform quantities?
Absolutely, yeah. I'm very new to this, but I think it's, first of all, a lot of fun to explore them. And I think that specifically, there can be a very fruitful interplay and something to learn. I think it's an unusual situation probably for people who study Laplace transforms to study them in the context where we have a specific alphabet, like the remainder function alphabet. What are the relevant Laplace transforms there? And maybe just make one particular comment. I don't have a feeling for how easy or difficult it is to compute this Laplace kernel, but let me just say this. If you're thinking of using this property to approximate something, I think this could be a very useful representation because by the theorem, this representation incorporates for you the infinite number of constraints that I was talking about. So if you have this representation, you don't have to impose individually the positivity of this or that derivative. So it's a very neat way of thinking about this feature.
Thank you very much for this great talk. Is there a notion of extremal, completely monotonic functions? So something in terms of which you know that if a function is CM, it has to be a positive combination of those?
Yeah, that's a great question. I suspect the answer is yes, well, I mean, I'm pretty sure the answer is yes. I would love to know how to use it. And let me give you a particular example. Which came up in this proof of a remainder function. So we're able to prove that this curly E function is CM. And there's an open question for me at 2 loops whether the remainder function is CM or not. So the typical situation is you have some quantity which looks like A plus B. You're able to prove that A plus B is good, but that B is positive. But so this A is also okay. That's a little bit less positive. So that's a way of phrasing in a pedestrian way your question about minimality. I think that's very relevant for many applications of this property.
Thanks for the nice talk. Is there a basis for these CM functions with which one could maybe write down an ansatz for any of these quantities?
Yeah, it's a great question. I mean, we're really exploring it. I I think it depends a bit on the context, because so it's related to what I just said. In some situations you have a CM function, and you might want to ask, is it minimal? Can you subtract something off of it? And I don't know. For example, if you have 1 over x on the unit interval, for example, then that's always bigger than 1. So you could also consider 1 over x minus 1. But then, so you mentioned bases. Basis might also involve the notion of integrating and having transcendental functions and so on. So for example, then it makes a big difference in terms of, do we talk about pure transcendental functions or functions of mixed weight? So then you could ask your question in different ways. So you could ask, is there a basis of pure functions at a given weight? Or do you allow also some rational algebraic functions? And I think depending on the case, you might get a different answer. But I think it's a very interesting question.
Okay, one final question.
Hi, thanks for the very nice presentation. I just wanted to comment adding a couple of examples to your list of completely monotonic functions. So there was an interesting paper by Tom Hartman and Greg Mathies, in which they were studying the C theorem in two-dimensional QFTs. And they showed that the C function can be chosen to be completely monotonic, non-perturbatively.
Oh, fantastic. Mm-hmm.
And another example is actually a paper I worked on with some collaborators in scattering amplitudes for systems at finite density. And there we found that the scattering amplitudes of excitations of a superfluid satisfy the completely monotonicity property, like for arbitrary densities, but in a specific model, we were able to check that it's satisfied, but we don't have an underlying reason for it. So I think it's interesting to...
That's very interesting. Thanks so much for the comment. Could you please send me an email with the references?
Of course.
Thank you so much.